So this evening, the topic is organic synthesis, past, present, and future, with our friend Ari Koskinen. He received his MSc in 1979, his licentiate in technology in 1982, and his Doctor of Technology in 1983 from Helsinki University of Technology. And after postdoctoral studies at the University of California, Berkeley, he accepted an appointment as a project leader in new drug development at the Orion Corporation Fermion in Finland, where his research group were among the first in Scandinavia to adopt a computer-aided drug design, as well as computerized database handling protocols in new lead identification. He returned to academia via the University of Surrey as a lecturer in 1989, and was then appointed as a professor of chemistry, especially synthetic organic chemistry, at the University of Oulu. Does that sound right? Oulu.
About Oulu.
Oulu in Finland in 1992, and transferred to Helsinki University of Technology in 1999, now Aalto University, as Professor of Organic Chemistry. He's a member of the Finnish Academy of Sciences and Letters since 2003, and he is the author or co-author of some 190 publications, 15 patents and 3 books. He retired from active academic work in October 2021, but as Emeritus Professor, he keeps his finger on the pulse of organic chemistry through activities in IUPAC as President of the Division of Organic and Biomolecular Chemistry, and in UCHEMS, which is the European, as was known as European Chemical Society, as a past Secretary of the Division of Organic Chemistry. And of course, he's also a member of the RSC Belgium Committee since 2024. So, Ari, over to you.
Thank you, Tim. I'm going to give a rather sort of personal view of organic synthesis, and I'm going to start with going back to about 35 years, prompted by a question Fabio asked me, do you want some water to drink with? And I said, no, thank you. Then he asked me, do you want some wine? And I said, no, thank you. And that reminded me of probably one of my first lectures that I gave abroad in Montevideo in Uruguay in 1990, I think, or 1989, 1990, about that time, when the local chairman asked me, so do you want something to drink? And I said, no thanks, I'm fine. And then he said, well, you know, we have had synthetic organic chemists giving talks here, and for instance, when Bob Woodward was giving a talk, he consumed a bottle of whiskey, so he opened up a cupboard and asked me, do you want a bottle of whiskey? I said, no thank you. The lecture room was packed. There was about 40 or 50 people, and I was astonished because I thought that Uruguay is a small country and the University of Montevideo would probably be a small one, but it was fully packed. And I guess about 40, 50 people, and I think I was the only person who didn't smoke during my lecture. Well, times have changed. As Tim said, after my postdoc, I basically started my career in industry. I was a youngster, about 29 years of age, when I was hired by the Finnish pharmaceutical company to start up a group of new drug development. And because of my background at the University of California, I had come to terms with people who were developing computer-aided methods, database management things, structural elucidation methods, drawing molecular structures. In those days, things like ChemDraw didn't exist basically at all. So we had to manipulate structures somehow to get them onto the computer. And at Orion, we still played the same game. I had a group of 10 people working with me. Just think about that, a 29-year-old guy having a group of 10 people working for him, 6 of whom were already also PhDs. So we had a fun time, you might imagine. The company gave us free hands in buying all kinds of computer things, and we very soon learned many methods, to which I'll come back at the end of the lecture when I'm coming back to the modern things of computer-aided structural design and modern computer-aided synthesis design and things like that. How things have changed over the past 40 years or something like that. But before we go there, we have to start with like I always do, with history. So we go way back, almost 300 years. The first syntheses, the way we are describing them nowadays, were very, very simple in modern terms. Shale synthesis of prussic acid is probably the first chemical synthesis where your product, the end product, is basically an organic molecule. It contains hydrogen, carbon, and nitrogen, all organic elements. It's just missing oxygen, but we can forgive him that. Wöhler made oxalic acid in 1824. The same year, Gmelin made crosinic acid. Well, Gmelin is considered to be an inorganic chemist, so we don't count him. But then comes the important discovery. 1825, Faraday and Henry Hennell managed to make ethanol from ethylene. And we'll come back to that later on in the talk also. But remember, this is 1825, which is before organic chemistry existed if you read the textbooks, because every textbook says that Wöhler was the one who invented organic synthesis. No. Wöhler didn't invent organic synthesis. Wöhler basically proved by chemistry that vis vitalis, the life force, doesn't exist. He didn't do organic synthesis, but it's a remarkable achievement anyway. So we keep that in mind also when we go further in this thing. Kolbe's synthesis of acetic acid is considered to be one of the masterpieces also. The beginnings of the synthesis. I have a big thumb, I know. The beginnings of the synthesis were purely inorganic. I mean, getting from elemental carbon to carbon disulfide, carbon tetrachloroethylene. Photochemistry, sunlight. That's something modern and something coming up, because we are reinventing photochemistry at the moment again. And then you get trichloroacetic acid, and out of which we got the acetic acid by electrolysis, which is basically the best way and the most economical way of doing reductions, by taking electrons to do the reduction. That's the cheapest way of doing it, and it uses the fundamental source of reductive power, which we're only beginning to understand how to use that in modern electrochemical methods. But luckily we are learning to do that too. So what people have said about chemistry, although Faraday probably cannot be considered to be an organic chemist, but he was a chemist, he was a multi-scientist basically. And he said that chemistry is necessarily an experimental science. Today I had the privilege of discussing with a couple of students at the Louvain-la-Neuve chemistry department, and they came to me and asked me questions about what to do here and how to do this and blah blah blah. And I told them that there's a fundamental answer to basically all of your questions. There's one way to know. Try it. An experiment. It'll tell you what the truth is. No matter how many calculations and how much computing power you use, but the experiment proves what you can really do. David Reed in early 19th century, he said that there is no more eminently practical science than chemistry, which brings the facet of chemistry having always had the applications in it. That's why we have the International Union of Pure and Applied Chemistry. It's not an International Union of Chemistry, but it's pure and applied chemistry. It's not or, but it's and, because we always try to find applications for whatever we do. And then the term synthetical experiments was first used in the context of organic chemistry in 1849 by Musprat and Hoffmann, the German chemist Albert Hoffmann, who was the teacher of chemistry in England, and he was also the founder of the Royal Society of Chemistry. So there's a strong connection with European connection of organic chemistry in general and synthetic chemistry. We are in the middle of the 19th century, and many people forget that that was also the heydays of organometallic reactions. Organozinc chemistry was basically born in 1850, and if you think about it, it's only about 2.5 decades after the first organic synthesis had been performed, and people were already using organozinc chemistry. Franklin was the mastermind of that, and I asked some of my students to actually read carefully the Franklin paper, because we were using diethyl zinc as a reagent. And they came back to me and they said that this guy must have been crazy. I said, so what's your reasoning for that? And they said, well, this guy actually made and distilled 0.5 kilo of diethyl zinc. Now if you take 1 drop of diethyl zinc at the moment, without a syringe, without careful protection from air and especially from water, you get an explosion. But this guy distilled 0.5 kilo of that kind of material, and he still survived that. The first true organometallic reaction probably was performed a little bit later by Butlerov. I think he was at the University of Kazan then, and he actually used the organozinc reagents to react with acid chlorides to make tertiary alcohols. A beautiful and a useful reaction even nowadays. So the birth of synthesis, if we ignore at the moment for a while the ethanol synthesis, definitely Friedrich Wöhler's synthesis of urea was at the forefront. Kolbe's acetic acid synthesis was at the forefront. We have to remember William Perkin, who was synthesizing cinnamic acid already in 1868. He's probably best known for his synthesis of mauve in attempts to try to synthesize anti-malarial compounds under the tutelage of Hoffman. Well, it didn't turn out to be anything anti-malarial, but it was a beautiful colored compound, mauvine, which Queen Victoria fell in love with. Now, if you play tennis and if you go to Wimbledon, you see 2 colors, green and mauve. Green is the green grass, and mauve is the mauvine, the mauve color that had been just invented because Queen Victoria played tennis. He played tennis on grass courts, and she loved mauve colored clothes. The first synthesis performed on industrial scale were alizarin synthesis and indigo synthesis, dye compounds, which basically one could say that the synthesis of synthetic dye compounds basically changed around the complete dye industry, because dyes had been isolated basically from isolation from natural products, natural plants, flowers and indigo plants and so on. And then people realized that we can make them from basically from coal, and we can make them a lot cheaper. So that was part of the industrial revolution that was going on at the middle of the 19th century. We have to remember Berthelot, who synthesized camphor. The first synthesis of camphor was actually by Berthelot. There's something you can read about what he said and what he thought about chemistry and beliefs in general. We'll go back to the camphor synthesis because that's going to be central and crucial for us for the next couple of slides. Camphor investigations provide an interesting episode because in those days people had isolated natural compounds like terebinthine, for instance. It's a terpene, so we forget that for a while. And Berthelot described that he could convert terebinthine to a hydrochloride salt, which basically, to us modern chemists, it says that okay, terebinthine must have been a basic compound because it forms a salt with an acid. and upon treatment with the base, which we normally associate with liberating the base from the salt, it gave terrecamphene, a different compound from the original terebinthine. And then when they oxidized terebinthine, they got camphor. Okay, so that was basically a total synthesis of camphor from another natural compound. But the interesting thing was that when they took not terebinthine, but when they took the L-pinene, which was also called terebinthine, but it had the opposite sign of rotation of polarized light. When they took this L-terebinthine, they got L-terrecamphene, which we nowadays call L-camphene. And from D-pinene, which was called osrolene, they obtained D-ostrocamphene or D-camphene. So the two opposite enantiomers of camphene, and from there on, for the oxidation, two opposite enantiomers of camphor. Today we know that the L form of pinene occurs mainly in the old world, where you get L-pinene isolated from the pine trees. In Europe we get the L form, and when you go to Canadian sources of pinene, you actually obtain the opposite enantiomer of pinene. Now that's an interesting case of geopolitical chemistry, I think. Whether you have left-hand or right-hand molecules. Yeah. But to put that camphor synthesis in pictures, what happened? L-pinene and D-pinene, or terebinthine or osrolene, they are not bases. They are not basic compounds at all. They don't have a nitrogen atom or anything basic in them. They have a base, a Lewis base, a double bond, which reacts with an acid, a strong acid, HCl, to form an addition compound. When you treat the addition compound, the chloride here, with a strong base at elevated temperatures, you kick out the chlorine, you get a carbocation, and you get a rearrangement product from that. And that rearrangement product produces stereospecifically either L-camphene or D-camphene. And then the magic thing comes here again. It's the oxidation of L-camphene with air and platinum black, which was an oxidation method that was developed by Brunstedt in Sweden originally. When you applied that chemistry to camphene, you get L-camphor. So that was definitely a total synthesis of a natural product from simpler starting materials that could be commercially available. Definitely fulfills the criteria of total synthesis in modern terms. That we could say that didn't lead to anywhere. Well, it did lead to anywhere. It led to people trying to make camphene or camphor using synthetic methods, fully synthetic methods. And now we are turning a little bit later. We are turning to the change of century from the 19th to 20th century. And what was the reason why people got interested in camphor again? Camphor had been obtained mainly from Korea, and the Korean forests were they were utilized by Japanese. And at the same time, in those days, there was the Japanese-Russian War, which blocked the transport of any products from Korea by ships to Europe or America. Camphor was needed for many things, and especially for gunpowders. And that came in during the American Revolution first, but then it was used to sort of moderate the explosive power of gunpowder, so that it wouldn't explode just haphazardly, but you could get a controlled explosion by the use of camphor. Then people realized that instead of making gunpowder out of it, you can also make billiard balls. Billiard balls everybody knows nowadays, but people forget the gunpowder connection there at all. But it had been a very important connection, because in many cases the developments of science and technology usually are connected with wars and disasters, sadly. So Kompa was the teacher, the first professor of organic chemistry at the Helsinki University of Technology, which is the symbol of the university is on the left-hand side here. That is the emblem of the Technical University or Helsinki University of Technology. Kompa was the first professor of organic chemistry there. He was professor number 4 at the university, where they had 12 professors altogether in the beginnings, and that was my last position. I was the last professor number 4 at the university before the university changed its name to Aalto University. I keep this picture here because I want to show you how important it was that the professors had they had style. A 3-piece suit, a cravat or a bow tie, every day fresh flowers on the podium. They were using chalk on blackboards, and they always had their senior assistant with them, because when Kompa had filled the blackboard with chemical structures and talks, he would knock on the blackboard, and the senior assistant, in this case this guy Sulo Viljakka, he came and he wiped off the blackboard so that the professor could use it again. I tried to suggest that to the university administration, but they said no. I don't know why.
You didn't get one?
No fresh flowers, no blackboards anymore. They even took out the whiteboards from us. Yeah, we could only use PowerPoints. So now we are about 100 years ago. The development of synthetic chemistry started to develop very quickly. The first synthesis of any natural product was the camphor synthesis by Kompa. William Perkins synthesized terpineol. The following year, Robinson's synthesis of tropinol came very soon. Bachmann's synthesis of a steroid, an equilinine, came very soon, also before the Second World War. So the era of change of chemistry from coal-based chemistry to oil-based chemistry started to show up quite quickly here too. And again, there's a connection with wars, because during the First World War, a lot of European chemistry was still based on coal. The Americans had found oil, and they started to make rubber and things like that from oil. Then they built cars, and they realized that, okay, since we have cars, we can make petrol, and with petrol we can refine the petrol into some other products also. The first polymers came out, the monomers for polymers came out in the 30s, and everything changed. Then the Americans sold the cars to Europeans, and the Europeans realized that, okay, within a span of less than 10 years, the numbers of cars multiplied by at least tenfold in Europe, which also meant that the need for crude oil, became huge, and coal industry was basically moved back to basically using coal as a reducing agent for making steel, which the Chinese and the Japanese Indians have taken away from us nowadays, sadly. During the same time between the world wars, we know Paul Dirac, the famous theoretical scientist, theoretical physicist. He said in one of his key papers, he said that the underlying physical laws necessary for the mathematical theory of large part of physics and the whole of chemistry are thus completely known. So about 100 years ago, he predicted that there's no more room for chemistry because you can calculate everything. Well, is that true? Maybe. Andrew Lu and Mark Mueller, almost 100 years later, they warned that the physics envy may be hazardous to your wealth it should be possible to build molecules of economic systems that are as predictive as those in physics. But the physics envy has also created a false sense of mathematical precision in some cases. And they want that the chemists using physics to explain chemistry is as dangerous as physicists using chemistry to explain physics to physicists. So these two branches of science, they are important, they are interrelated, but you can't explain one by another. And this is actually an even earlier one. Sidgwick had said this already in 1933. About the same time, this is from Cornell University Press, in the 1930s, Roger Adams from Harvard University said that because of the developments of natural product synthesis, total synthesis, which we have seen the simple compounds now, he already said that by the end of 1930s, there probably is no need for total synthesis anymore, because we can make, a synthetic chemist can make almost every possible molecule. About 100 years ago, almost 100 years ago. Interesting. So then we had the Second World War, the sophistication increases, we learn detailed mechanisms thanks to the physical chemists and physics in general. We learned a completely new branch of chemistry, conformational analysis by Derek Barton and Ole Odd Hassel from Norway. Spectroscopy basically was also invented or brought into practical use in those days. There were a couple of papers which utilized things like IR already in the 1940s, but it wasn't a common thing in the practical chemical laboratories. From the 1950s, you can still find papers where they had IR spectra actually produced in the publication, so that people could look at the IR spectra from the published papers. Nowadays, if you try to put in a listing of IR resonances in the paper, the editor will probably just wipe it out, because you don't need it. It's got to be somewhere in the supplementary materials. And chromatography came to the chemistry labs also about the same time. First paper chromatography, then we could put them onto the columns, and that developed very quickly into column chromatography, HPLCs and so on. But that was basically when I was a beginning PhD student in late 70s, HPLC had just come into practice. So that's about 50 years ago. And then what really revolutionized the synthesis in those days was the development of selective reagents. If you look at the catalogs of commonly used reagents at the moment, most of them, or their predecessors, the simple versions of them, they were developed in the 1950s, 1960s. Of course, now some people still use reagents like aluminum chloride or lithium aluminum hydride, which are strongly discouraged nowadays because there are more environmentally benign compounds existing. But still, they came from the 1940s, 1950s, maybe 1960s. LDA was invented in 1974, so that's a really, really recent, basically, invention. So that is also reflected in the target molecules of total synthesis. Quinine by Woodward in 1944, vitamin A by Otto Isler in 1949, and Woodward's name comes up again with prednisone, strychnine. I'll say a few words about that in a bit. In 1954, synthesis of morphine in 1956, which is a fantastic year because Istvan Marko and myself were born in that year. Woodward's reserpine synthesis, which is still considered to be one of the most beautiful masterpieces of design of synthesis, is also from that same period. And the first total synthesis of penicillin V by Zhang Xian in 1957. So these are rather complex looking molecules already compared to the original simple urea and so on. And then things got even worse. We got all these spectroscopical methods, the chromatographic methods, so people could isolate more and more complex molecules from natural sources. Longylpholine came out, prostaglandins, which were isolated in quantities of less than milligram quantities, and their structures were elucidated by total synthesis, because that was the only way you could prove a stereochemistry of, for instance, these alcohol substituents here, by actually making all possible stereoisomers and then comparing which ones of them were the real natural products. I met one of the people who were working in E.J. Cover's group in 1980, still working on not prostaglandins but the similar compounds in 1980s, and he said that he started an 11-step total synthesis of one of the natural products with 11 milligrams of starting material, and he ended up with less than 1 milligram of final product, which was in those days, in the 1980s, you couldn't run an NMR spectrum of 1 milligram of compound. You needed at least 20 milligrams of compound to get an NMR spectrum. So how did you prove your product? By comparing the UV spectrum. And then some people said to me already 20 years ago that, well, nobody uses UV spectra anymore, and I always took up this example, and then I said that okay, and besides, practically every synthetic chemist uses UV spectroscopy every day. When you take a TLC plate and you visualize your spots under UV light, you do UV spectroscopy. So things got worse and worse as you look at the structures. They're getting estrone, which is one of the steroids. It's got more stereocenters than we had in the equilinane synthesis. Prostaglandins, isocomine, basically no functional groups except for the one poor double bond here, otherwise very difficult to realize what the molecule is. Spectroscopically difficult to see. Yoshito Kishi started to work on multiply oxidized compounds and multiple stereocenters. Periplanone by Clark Still in 1979, thionomycin, and I say here Merck because this was actually a synthesis which was developed at Merck pharmaceutical company by Bert Christensen and his friends, and it's an industrial synthesis of this compound which involves 14 chemical steps. Out of those 14 chemical steps, 6 were already organometallic. One actually is a carbene insertion, which was in 1980. A carbene insertion was like a magic word in those days. Maytansine, multiply stereochemistries in there, and then 1980s, 1990s, you can start to see the explosion basically of the complexity of the molecules. Amphotericine, calicamycin, rapamycin, brevetoxin, avermectin, endriandic acid, Taxol, and you see one name there, Casey Nicolau, very prominently, practically showing the borders of organic synthesis, how far you can take them. And then we come to the last picture of these funny looking molecules. You have the world record of complexity, I think, at the moment, matotoxin, which has basically 99 stereocenters in the molecule. Immensely complex molecule. It hasn't been synthesized so far, but you can guess who's trying to synthesize it. It's one Nicolau again. Palitoxin has been synthesized by total synthesis. It's got 63 stereocenters, so it's an immensely difficult molecule, and it has been synthesized by Yoshito Kishi from Harvard University. There are other compounds. Alicandrine has been synthesized. Zolxentelatoxin and its related compounds have been isolated by Daisuke Uemura from Japan. And he said to me a couple of years ago that they are actually working on structures of very similar compounds, and they believe that they are twice as complex as the zooxanthellae toxin. I don't know where they are at the moment. They haven't published anything over the past couple of years. So to put everything in a pictorial form, the complexity of the target molecules for synthesis, total synthesis, they have been developed, or they have been increasing immensely. In the 1820s, if we take the urea synthesis as the starting point, no stereocenters, zero stereocenters, then alizarin synthesis in 1868, zero stereocenters, camphor total synthesis, 2 independent stereocenters, and that we have already gone 80 years, 75 years in the development. Then we come to strychnine by Woodward, 1954, and we're still less than 10 stereocenters. Then we go from that to erythromycin, about 20 stereocenters, 1979, and 1994 to palidoxin. And if you look at this curve, it basically looks like an exponential growth of selectivity. So I showed this to some of my students in early 2000s, and I said that okay, if we look at the target molecules that you should be synthesizing, you should be following the exponential growth here, and by 2005 you should be making compounds which have at least the number of stereocenters as matotoxin has, at least 100, and that should be a piece of cake for you. Now, has that happened? I think mid-1990s something happened in the world, and I have said it often, and some people don't like it the way I say it, but I think creativity died. Not only in chemistry, but in many fields of human endeavor. Arts, music, the creativity was replaced by something else, by a thing they call productivity at the moment. It's more important that you produce more in quantity than more in quality. And that is something that is reflected in today. And then we go back to the last articles, which were basically defending total synthesis. Corey's Nobel lecture, The Logic of Chemical Synthesis, Multi-step Synthesis of Complex Carbogenic Molecules, 1990. Or Clayton Heathcock organized a meeting, the so-called Ravello meeting, where people working in synthesis in mid-1990s they were discussing, as we head into the 24th century, is there still value in total synthesis of natural products as a research endeavor at all? Dieter Seebach wrote a paper in Angewandte about the same time in 1990s, Organic Synthesis, Quo Vadis, where are you going? And they all came to the same conclusion, basically, that there still is room for total synthesis. But many people misunderstand it by saying that the best value for total synthesis is for educational purposes, because it's the only way where you have to learn different techniques, not only making certain kinds of reactions, but to be able to change from one chemistry to another chemistry very fluently. Use spectroscopy as fluently as possible. Utilize computational methods as easily as possible. About that time, 1990s, early 2000s, combinatorial chemistry was emerging. So people started to realize that I can make a library of compounds easily by taking a number of related starting materials of one type and then related starting materials of another type, and combining them together, and basically I get a combinatorial library of molecules out of that. I met this guy, David Weininger. He was working at the Pomona College in California in those days, and I visited Pomona College and I had the pleasure of discussing with him, and he had a small, I think it's a Cessna, and this bearded guy took me to in his Cessna, and he took me to the Anaheim, where he did an Immelman on the what is it? The roller coaster thing. The forget the name of it. Mountaintop something. And he said that, have you ever done an Immelman? And I said, I have been in that roller coaster. And he said, have you ever done it in real life on a plane? And then he did one.
A loop?
Yeah, a loop, yeah. And he's the guy who actually basically invented a chemical language, the Smiles language. The Smiles code was written by him. And he tried to sell it to chemical abstract services, which didn't buy it, but then some other companies bought it, and we practically all organic chemists can read Smiles nowadays. Now there's an Inchi code nowadays coming from IUPAC, but this guy being a mathematically brilliant guy, I asked him a question. So, can you really? No, that is wrong direction. Can one make all conceivable molecules? And he said, okay, let's do some calculations. Let's assume that we make molecules which contain only organic elements: carbon, hydrogen, nitrogen, and oxygen. And then, because he was working at Pomona College on medicinal chemistry, he said that let's also restrict this so that we get calculable numbers to compounds which are permeable drug molecules that can pass through the cell membrane without active transport. So they should be round molecules, and they should have a molecular weight roughly about 500 Daltons, and let's put a maximum of, say, 750, so that we have a molecular weight distribution like a Gaussian curve centered on 500, basically. So that's the restriction. The number of molecules, when we can compute that, we have to remember the Avogadro's number, 10 to the power of 23. And if we only make one molecule of each compound, there are roughly about 10 to the power of 200 different molecules that could be made, with average molecular weight of 500 grams per mole divided by the Avogadro's number and so on. So if we make one molecule of each, we get a total mass of 10 to the power of 173 tons of material. That's a lot.
It's a lot.
The weight of Earth is 10 to the power of 21 tons. So if all the elements in the world were just carbon, hydrogen, nitrogen, and oxygen, we couldn't make any visible part of the molecules available. And then a little bit later on, I met a cosmologist from Princeton, and I asked him, so what's the total weight of the universe, including the black mass? And he said that it's probably about 10 to the power of 53 tons. So the whole universe is not enough, nowhere near enough to make just one example of all possible conceivable molecules. I told my students about this, and then somebody wrote on a whiteboard, there are not enough molecules, there are not enough atoms in the world. That's true. So basically, with the advent of combinatorial chemistry, we came to face the realization that you simply cannot make everything that you can conceive of. Just impossible. So what on earth should we do? We can't just try everything. Like I said to the students today, that the best thing you can do is just try the experiment, and the experiment will tell you whether it's true or not. But if you can't make an experiment because there are not enough atoms in the universe, realities of today, not today, this is a couple of months old, but a couple of months ago, the Chemical Abstract Services listed about 290 million inorganic and organic substances. When I was a first year undergraduate student in 1975, our inorganic chemistry teacher said that something remarkable has just happened. We just passed the line of 4 million known chemical compounds in the world. And that's gone from 4 million to 290 million. UniProt is a database which lists the protein sequences, and they say that there are about 60 million protein sequences known at the moment, isolated and sequenced and known by that. A couple of years ago, they gave a Nobel Prize on artificial intelligence, and one of the companies that got the Nobel Prize. Funny, they give Nobel Prizes to companies nowadays, but it's true. It's AlphaFold who got the Nobel Prize. They said that there are 214 million predicted protein sequences, so 4 times the amount that had been isolated and characterized. And today that number must be much more than 200 million, because the computational power has gone up from 2024. And at the same time, the chemical reactions, the number of chemical reactions, when I was a PhD student in my grad school, people were saying that if you learn about 2,000, 3,000 chemical reactions, their mechanisms, you understand all the organic chemistry. Today, there are roughly about 150 million single-step chemical reactions in the world, so nobody can remember that amount. Yesterday we were talking about the amount of literature also. When I was a PhD student, it was easy for anybody to follow 10 journals regularly. And I read Angewandte Chemie, JACS, JOC, Tetrahedron, Royal Society journals and so on, where JACS had published about 4,000 pages a year. Nowadays, they publish unknown number of pages because they don't have page numbers anymore. The last time I bothered to look at it, I realized that they must publish more than 400,000 sheets of A4 sheets of material in JACS alone. Now, who could read 400,000 pages of A sheet per year and still do something else, let alone follow 10 journals of the same kind? So the amount of information, or not information, the amount of data has multiplied so much that we don't even realize how much data there is in the world. That's why we have sources of data which we cannot even verify the value and truth of them anymore. There are no methods of doing that. And at the same time, we are saying that the news are full of misnews and false information. The world is full of false information. Organic synthesis has developed. We've seen this. It started from total organic synthesis or target-oriented synthesis. It came to the 1960s, the methodology-oriented synthesis, which gave us the tools so that we can be more and more efficient. Diversity-oriented synthesis came in the 1990s. Function-oriented synthesis in 2000s, and a little bit clearer presentation of this comes from Ryan Shenby, looking at the sort of different kinds of synthesis that we can do. The target-oriented synthesis is one where you have the sort of chemical descriptors. They can be anything, any properties of any molecule, whether it be boiling point, molecular weight, electronegativity, binding onto a receptor, any number that can represent a molecule. You can build an n-dimensional matrix, and then you can look at how the development of the synthesis goes there. You go from target-oriented synthesis, where you start from something simple, then you go step by step, and you go from one compound through single compounds to your target. There's no diversity basically in that synthesis. Divergent synthesis or divergent synthesis, you follow basically the same line until you get to a branching point. And this was something that came very proficient in the 1960s, 1970s, when the number of drug molecules increased so much. We started to have the first antibiotics. All the other companies developed their antibiotics. The first blood pressure regulating agents came out within a couple of years. All the pharmaceutical companies had their own blood pressure reducing agents. So that's basically the divergent synthesis. In a traditional combinatorial synthesis, you start from one compound and you make from one single compound, you make several different intermediates. Then you take the library of several different intermediates and you let the library react with another library of reagents, and you get a library of libraries. So you multiply the number of total targets. And then you have a diversity-oriented synthesis, which is basically a combination of the divergent synthesis and the traditional combinatorial synthesis, where you follow the original path to some point and then you explode from there to different values. So basically what you do is you cover a broader range of the chemical space. Instead of making just compounds which look like something similar to what we have been doing previously, you actually make a library of libraries which have completely different kinds of properties. Or to put it in another way, you can look at the natural product synthesis, which is like this, and that was the related to the target-oriented synthesis here. And then the combination of these ideas is that instead of trying to go to a natural product target, for instance the NP5, which is the NP5 here, whether you follow the target-oriented synthesis or divergent synthesis, instead of trying to find this compound, you somehow predict that there is a compound that has superior properties. And that brings in the molecular design, the calculations and mechanistic things and so on. Artificial intelligence, basically. So that you realize already from looking at the natural product target, you realize that if I change the target structure somehow, I actually do get a better target molecule. And then you develop basically a synthesis for that. And that can be still a relatively simple synthesis, a straightforward synthesis. I promised to get back to ethanol. I know it's not Friday today, but still, ethanol is so prominent in the world at the moment. Faraday's synthesis of ethanol was actually what they did in the UK was they actually took ethylene and reacted ethylene with vitriolic acid, sulfuric acid as we call it nowadays, and they got a salt. And then Faraday said to his student, Henry Hennell, that you take this salt and you go to France to some of my friends and you ask them whether they can figure out what the salt is. And in France, Henry Hennell figured out that the salt was actually the sodium salt of the ethyl sulfate. And when you hydrolyze that, you get ethanol. And that was the synthesis of ethanol. That they published, and that became the sort of, in my opinion, the first synthesis of a relatively complex organic molecule. In 1947, Shell patented a process where they take ethylene in large scales, water, a phosphoric acid catalyst, high pressure, high temperature, and they get ethanol. That's the industrial synthesis, industrial process of making ethanol, and it still is the most common chemical synthesis of ethanol, by which we make about 850,000 tons of ethanol in the world at the moment. That's why we have ethanol cars running on ethanol, or 15% of ethanol, or whatever they have.
Can that be used for drinking?
Not this one. The drinking ethanol is basically by fermentation,
Yeah.
which I think is better because we don't have the phosphoric acid in our alcohol.
Yeah, sulfuric acid.
Yeah. Or in absolute. You wouldn't want to have phosphoric acid in absolute.
No.
Now, the truth, I don't know about the amount of ethanol production at the moment because of the wars we are undergoing at the moment. I don't know what it is nowadays because during wartime ethanol consumption goes up, and that's not because of the soldiers need ethanol, but it's because their instruments and the war machines basically consume a lot of ethanol in that. And also the petrol consumption goes up. A couple of total syntheses here. Just a question. We come back to Roger Adams from Harvard, who had said that we don't need total synthesis. A couple of years later, in 1940, he took this starting material, which is you can make in a couple of steps from simple starting materials, and you can basically buy olivetol, which is a constituent of olive oil. You do a condensation between them, and then you do a Grignard reaction with methyl magnesium iodide, and you get tetrahydrocannabinol in 1940. It's basically a two-step chemical synthesis. In 1940, people would say that that's efficient, step efficient or whatever efficient. And then we come back from there, step forward 67 years, and we go to Stanford University. Barry Trost starts from olivetol, does a two-step conversion of olivetol into something else, does an organometallic reaction, does a second organometallic reaction, does a third reaction where they use sodium hydroxide, then LDA, then rhodium, then methyl lithium, then a truly inorganic reagent, a thiol, and then organometallic reaction again. Altogether 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 step synthesis to get to the same tetrahydrocannabinol. Now, is 10 steps more efficient than 3 steps? I don't think so. So we can ask the question which many people have asked, so where did our creativity go? We create more and more efficient, more cumbersome things. So the reason why we have done synthesis was to disprove the vital force and basically for analysis in the early 19th century. Synthesis proper, Grebes, industrialization in 20th century, early 20th century, structural proof because there were no analytical methods. Birth of big pharma was in the beginnings of the 20th century, late 20th century. Then we started the explosion of biologically active compounds, new materials, nanotechnology, CombiChem, organic catalysis, microwaves, flow chemistry, all these things, they came within the past 20, 25 years. I'll skip this strychnine synthesis because these are just illustrations of how we have gone from relatively straightforward to relatively complex and back to this. I think this is a beautiful example by Till Opatz that to make optically active strychnine it takes a total of 14 steps from basically commercial starting materials to get an optically active final product of strychnine, which was the Woodward's 1954 showcase. Molecular modeling started practically in the 1960s already, although people very often say that Frodo was the first molecular modeling program that was developed, but it was actually developed by Cyrus Leventhal and Bob Langridge, who were working in Leventhal in MIT and Langridge at Harvard, and they used cathode ray tubes to display structures of X-ray structures of molecules. This was the beginnings of molecular modeling, basically, and computer graphics, because soon they could manipulate the graphics or the structures on the cathode ray tubes. You could rotate them around and you could see the three-dimensional structure quite quickly. It took almost 20 years before that was commercialized in computer games. It's basically using the same algorithms, but it was the chemists who came up with these ideas first. The chemists also came up with the ideas of computer-aided synthesis design or synthesis prediction in the 1980s. This is from a reagents system. It could actually be already from one of the things that we did in the company where I was working, because we were the first ones to use reagents in Europe, because I happened to know the guys who developed the codes, and they gave it to us free. But these were the kinds of computer graphics that we were looking at 10, 40 years ago. Quite different from what we see today. What are the future trends? And that's very difficult to predict the future, because it's almost as difficult as one historian said, that nothing is more difficult to predict than the future, except that the past in Soviet Union. Automation, definitely it's gonna change many things. We have flow chemistry. It's changed completely from what it began about 15-20 years ago. It's completely automated nowadays. There are actually plants that can make substantial amounts of relatively complex medicinal compounds by automated flow synthesis. You combine that with things like photochemistry, photochemical cells that have been developed so that you can use them in flow chemistry. 10 years ago somebody criticized the flow chemistry, that you can't do flow chemistry or photochemistry in flow mode because the Lambert-Beer law. You just can't pass the energy deep enough in the flow cell. Now that can be solved very easily. So instead of using a single flow cell, you use a multiple cell. You use multiple flow reactors basically side by side. Electrochemistry, that has been developed into flow mode already. Synthesis planning, can that be done? People are saying that artificial intelligence, machine learning, deep learning, these are giving us the methods of synthesis planning. But there's always the problem. These are based on existing data. But is it validated? Because the validation is something that is missing at the moment. And also the databases which contain the poor experiments that give you poor results. Because nobody publishes at the moment that we tried to make this but it didn't work. Combination of these, robotics. Definitely that is something that will come soon, or sooner or later. We already have miniature robotic systems where you can have, for instance, I just learned very recently, about 2 weeks ago, that there have been commercialized already systems where you can monitor your blood sugar levels without contact, basically, without taking blood samples at all. You basically have a camera which you can connect to your mobile phone, and the camera basically measures using near IR spectroscopy. It measures the oxidation levels of iron 2 and iron 3 in your hemoglobin, and that correlates directly to your insulin levels. And that information can be fed into your miniature computer, which can be an implant somewhere in your body. And when the levels of insulin change in your body, the small processor can tell 3 different sources of starting materials in your body, close to your pancreas, that okay, you have to start your insulin synthesis now, and instantaneously your artificial insulin synthesis machine corrects the insulin levels. And that's going to be fantastic when you can do that not only in insulin levels for diabetes, but also for things like blood pressure, when your ACE angiotensin converting enzyme levels are screwed up somehow. Again, the synthesis of the necessary compounds can be started. Within the next 20 years, all of these things will be changing tremendously. It's partly because we have the help of artificial intelligence and things like this, but I think it's going to be even more important that it's going to be based on synthesis, which means that we still have to develop more efficient total synthetic methods. Whether they are of molecules with 1 million stereocenters or whether they are simpler compounds, it doesn't matter. But there still is room and need for total synthesis. I don't know whether I answered the question that I put in my synopsis, but I firmly believe that there is room for total synthesis.
Okay.
Thank you.
Any questions? I thought there were a few things about philosophical points indeed as well.
You mentioned that there's an enormous amount of information and data around.
Yeah.
But unfortunately it doesn't seem to correlate with a greater amount of comprehension.
Confidential.
No, comprehension.
Comprehension. No. And I used the wrong word. Not information. We have a little bit of information. We have a lot of data.
Yeah.
But, the amount of information to convert data into information requires comprehension. And I think that's something that is missing.
To talk about the information, can a professor today program intelligence, artificial intelligence program for his fields of interest, so that it reads all these papers and then give him a condensed summary of what could be interesting for you as professor?
In principle, yeah. It's something I discussed. My youngest child, he's studying history at the moment, not sciences at all. And we had an interesting discussion with him a couple of days ago about the value of artificial intelligence in fields like history and literature in general. And he was saying that, again, nothing much has changed except the speed at which we can produce useless data. We used to have cheap literature. In the 1970s, you could go to a bookstore and you could buy a classic book, and you would have to pay for that, let's say, 30 units of money. Or you could go to a kiosk and buy kiosk literature, which was basically love novels or war novels or whatever, and you could pay 1 unit of money for that. But still, I would say that the classical literature and the kiosk literature are on completely different levels. You can't compare them. And the same way with artificial intelligence. With artificial intelligence, what it does is it takes the stochastic and basically stochastic algorithms and uses existing data to search out the kind of information that your program way tells it to look for.
Yeah.
But it doesn't mean that it creates anything.
Yeah, it's one of those misnomers. There's very little intelligence in artificial intelligence.
Yeah.
So it's actually it's a predictive text a machine on steroids, effectively at the moment. I mean, it may evolve to get some intelligence within it, but currently it isn't.
Yeah. I think somebody said about our artificial intelligence that artificial intelligence is a misnomer.
Yeah.
There's no artificial and there's no intelligence.
But it's in charge currently.
Yeah.
So.
But it's an extremely powerful method when you have a huge amount of data. That came in when we got all these quick methods of analyzing things. When people realized that a human being simply cannot analyze that amount of data anymore. You have to have an algorithm that goes through it. We had, as an example, we had in the beginning of this millennium, I had a PhD student, a master's student, who was working in a project where we were trying to develop an organometallic system where we had a metal center of certain metals together with ligands of certain types, and we wanted to scan through the X-ray structures of anything that were related to those compounds. And I said to this guy that, look, there's this Cambridge database of X-ray structures. Why don't you take that and write, since you have been studying computing, write an algorithm that will simply go through all the data and search out from there the structures that meet our criteria, and then tell the algorithm to analyze them and cluster them into certain types of different types of metal ligand combinations. And he wrote a code for that, and he solved this problem in about less than 2 months. And that was a master's student. A huge amount of data at that time. Now, this is the power of computation. You can take huge amounts of data and you can learn from that data, but still, in the end, you need somebody to actually go through the results and say that, okay, this is something that we can use, or this is just bullshit.
Yeah. That's a problem with many fields currently, is that no one is. They just take it as gospel what AI comes and tells them, and you need someone to give it a sore thumb at the very least to see what's what and what isn't. Any more questions?
I have one more question.
Yeah.
You talked about the number of molecules, but how many molecules are actually useful for something, where there is an application for them? Do we have 1 million molecules that we can
No.
do something good with? Or?
Depends on many things. I've read recently data from pharmaceutical compounds that there are roughly about 10,000-15,000 pharmaceutically active compounds. But when you look at the molecule or the pharmaceutical products that are on the market, it's basically throughout the world is based on roughly about 1,500 different compounds. The REACH database, which contains all the industrially important compounds, I think they are listing at the moment something on the order of maybe 50,000 compounds.
Yeah.
So we are living in a world where we are utilizing only a small proportion of the molecules that have been made or that have even been made on industrial scale. And that's changing also because we are losing a lot of chemicals at the moment because of these incentives like REACH, for instance. Many academic laboratories are still using halogen-containing organic solvents, which I would fairly say that in my group, before I retired, we forbade the students to use halogenated solvents. And I told them that simply because it's not safe. You have to figure out another way of doing safe chemistry.
Yeah, it's not safe for the students, let alone anyone else. Yeah. Okay. Well, thank you very much, Ari, for your
My pleasure.
for the talk. Yeah, we'll have a few